how we can represent both analysis and synthesis equations of DFT in the matrix form. And we also discussed that matrix inversion can be avoided or replaced by a conjugate of the same matrix divided by n while solving synthesis equation of DFT. Now in this lecture, we will perform computational analysis of n-point DFT equation, which means that when we will implement n-point DFT equation on our computer, then how many computations will be performed by our computer in order to provide the result of n-point DFT output. As we already know, n-point DFT equation takes n number of time domain samples as an input. It will process them and it will provide n number of samples as an output in the frequency domain. But in providing those n number of samples in frequency domain, how much computational workload will be on our computer or how many computations will be needed to perform by our computer, we have to investigate this thing. And it is very important to understand because whenever we implement any algorithm on our computer, we must have to take into account their computational requirements so that we can conclude can we process our signals to that technique in real time or not. So in this lecture, we will find computational cost or computational complexity of the n-point DFT equation. Now, if you recall the equation of DFT, which is simply equal to summation x of n into exponential minus j 2 pi k into small n divided by capital N, then you will find only two operations in the DFT equation, which are multiplication and addition. So performing computational analysis of DFT means we have to find how many multiplications and how many additions will be performed by our computer while solving the n-point DFT equation. So these are the computational factors of n-point DFT equation: number of multiplications and number of additions operations. Now the multiplication and addition operations can further be classified into two types of computations, which are complex computations and real computations, which means that complex computations includes both complex multiplication and complex additions, while real computations includes both real multiplications and real additions. So performing computational analysis of n-point DFT equation means we have to find the total number of complex multiplications, complex additions, real multiplications and real additions performed by our computer in providing the result of n-point DFT equation. So the basic objective of this lecture is to find the requirement of these four types of computations for an n-point DFT equation. Now, before performing computational analysis of n-point DFT, let's start with some very basic examples so that you get an idea about what we will do in the n-point DFT case. So you are provided with some numbers along with some mathematical operations, and your task is to identify the type of computation and the number of computations involved in each case. So I hope all of you can very easily identify both the type of computation and the number of computations involved in each case. So in the first case, which is simply 2 plus 3, it is simply a one real addition operation. Why it's a real addition operation? Because we are adding two real numbers. For addition operation, we need two numbers which are real by nature. So the quantity of or the number of addition operations is simply 1, while the type of addition operation is simply real addition. Now in the second case, it is simply a one real multiplication because we have multiplied two real numbers. So it's a one real multiplication operation. And in this example, it is a one real addition and one real multiplication operation. Now let's come to the case of complex computation. Suppose this is the first complex number and this is the second complex number, having some real and imaginary part in both cases, and we want to add them. So the type of computation is complex addition, and the number of complex addition is simply 1 because we want to add two complex numbers. But you must know this thing, our computers cannot add complex numbers directly. In order to provide the result of the complex addition of these two complex numbers, we must have to add A into C and B into D. Now, when we will add A into C, we will get some number which is represented by E. It could be any value. Similarly, when we will add B into D, we will get another number which is represented by F, and this plus J will remain as it is. So the answer of the addition of two complex numbers is another complex number. But how we have obtained this result? In order to get this final result, how many additions we have performed and what was the type of computation? Now, as you can see, how we have obtained this E value, we have added A into C. So this was a one real addition operation because A and C both are real numbers. So this is the first real addition operation. Similarly, how we have obtained the value of F, we have added B into D. So this was another real addition operation, which means that one complex addition is equivalent to two real addition operations. Whenever it is required to perform one complex addition operation, it means that our computer will be needed to perform two real addition operations in order to provide the final result. We have to add A into C, and similarly we have to add B into D, which will make it two real additions operations. Now let's come to the fourth type of computation, which is complex multiplication. Suppose we have two complex numbers which we want to multiply. So this is the one complex multiplication operation, but again our computer cannot multiply these two complex numbers directly. In order to get the final result of the multiplication of these two complex numbers, the computations will be performed in the form of real computations. So let's see how many real computations will be involved while multiplying two complex numbers. So just multiply these two complex numbers. So on multiplying these two complex numbers and then rearranging their terms, we will get this one, AC minus BD plus J AD plus BC, which can further be simplified in order to get the final result. AC minus BD will make the real part of the final complex number, and AD plus BC will provide the imaginary part or the imaginary value of the final complex number. So the result of the multiplication of two complex numbers is again another complex number, but how we have obtained this value, we have to count and identify the type of computations involved during multiplying two complex numbers. So basically we have multiplied A with C, B into D, A into D and B into C. So this is the first multiplication operation, this is the second one, this is the third one, and this is the fourth one. So basically we have multiplied four real numbers while solving one complex multiplication operation. So we can simply say that one complex multiplication has four real multiplications operations. Now let's come to the addition operations. In order to get the final result, we have performed two additions. The first addition was performed here when we have added the result of AC with BD, and this subtraction is basically a kind of addition for our computer. So this is the first addition operation. Similarly, we have added the result of AD with BC, so this was another addition operation. So first real addition, second real addition, which means that one complex multiplication has two real addition operations. So the thing to remember is that whenever it is required to perform single complex multiplication or one complex multiplication operations, our computer will need to perform four real multiplication and two real additions in order to provide the result of one complex multiplication.